So as our little lesson today, we are going to review a couple of reaction types and really look at why we use the balanced chemical equation. And we're going to use a little stockroom-based scenario to look at these concepts. So I do have this bottle in my stockroom, and most of the time, the bottles in my chemical stockroom are labeled with their concentration, or what's called their molarity. Molarity, which is the unit is a capital M, is just the number of moles of solid dissolved to make a liter of the solution. So for example, I could make 1.0 molar sodium chloride solution. I would take 58.4 grams, because that's the mass of 1 mole of sodium chloride, and I would dissolve it in a little less than a liter of water because the sodium chloride is matter. It does take up space. This bottle of barium chloride, though, is unusual because it just says X molar. And so I'd really like to think about how I could figure out how many moles of barium chloride were used to make this solution. Well, I'm a chemistry teacher in a chemistry classroom, so the first thing I think of is how could I use chemistry to do this? Could I use a chemical reaction? And the two biggest types of reactions we've studied were, of course, redox reactions and ion swaps. So maybe I could use one of those. So let's think about using a redox reaction first. In a solution of barium chloride, I have barium 2 plus ions and 2 chloride minus ions floating around dissolved in the solution. So maybe I could use a single replacement reaction. Remember, in a single replacement reaction, an active metal replaces an ion that's in solution. So maybe if I could find a metal that was more active than the barium, it could kick out the barium, make barium metal, and I would have a solution of something else. Whenever we have a single replacement reaction, though, we look at our activity series to think about how it's going to work. So here is the activity series, just like it is on the back of our table or the JAG-iotic table. And of course, the higher up we are on the activity series, the more active it is. And we need a more active metal to kick the barium ions out and turn them into barium metal. That might be a bit of a problem looking at the activity series here. Barium is the third thing from the very top. It is an extremely active metal. In fact, the only two metals I've got on this list that are more active would be lithium metal or potassium metal. And both of those react rapidly and energetically with water. So if I put potassium metal in water, it's more likely to react with the water molecules than it is before it even finds a barium ion to interact with. So maybe a redox reaction isn't going to be a very good choice. So what if I used an ion swap? Of course, ion swaps come in two varieties: acid-base reactions and precipitation reactions. And looking at the fact that we're dealing with barium chloride, that's not an acid or a base, so we sure can't use an acid-base reaction without an acid or a base. So we're going to have to think about maybe how we could use this in a precipitation reaction to make a solid. Well, time to pull out our periodic tables and take a look at the solubility rules. And of course, I have those here on the slide. These are the same ones on the back of your periodic table, and basically the same as what's on our JAG-iotic table. Just in both places, those are organized by the anion. So since I have barium chloride, I'd look for the chloride ion. It's under the things which are usually soluble, but it will form a precipitate if it reacts with silver, lead, or mercury. So maybe I could make this chloride ion into a solid. Then I could separate the solid from the solution that's left over. And if I can measure the solid, like get the mass of it, maybe I could use that formula of whatever I made to figure out how much chloride ion did I have to have in order to make that much solid. So I have three options here, but I have a problem with two of them. Both lead and mercury are toxic, and both of them require specialized, expensive disposal to keep people and the environment safe. So I don't think I want to use lead or mercury. I do have silver nitrate in the stockroom, but the problem is it's really expensive, and I don't want to waste it. So is there a way that I could maybe predict how much silver nitrate I need so that I don't put a bunch of extra in and waste an expensive chemical? And in fact, this is one very, very useful function of the balanced chemical equation, which is part of why we spend so much time learning about balancing equations and types of reactions. How does the BCE help me? Well, I'd like to use an example that's maybe a little simpler for me to draw, and I'll show you. So here's a simpler BCE. This is a redox synthesis reaction, two elements coming together to make a single product. And of course, we know that the BCE tells us what's going on in a reaction on an atomic or molecular scale. So this tells me that two molecules, or four atoms, of hydrogen can react with one molecule, or two atoms, of O2, and it forms two molecules of water vapor. And that's great to know, but the problem is I can't measure atoms, so I need to scale this up somehow to something I can see, something I can measure. Well, let's try scaling it up a little bit first. Let's go to 10 oxygen molecules like I've got on the screen. 10 oxygen molecules is 20 oxygen atoms. And each one of those oxygen atoms matches up with an H2 to make H2O. So I guess I would need 20 H2 to react with the 10 O2s. And if I had that, then I could put that together and think about how many H2Os I would need. So I guess it would be 20. So it's really kind of the same ratio, only I've scaled it up to a bigger number. Instead of 2 to 1 to 2, I've got 20 to 10 to 20. Well, okay, but I still can't measure 20 molecules any better really than just one. So I'm gonna have to keep scaling up. Let's scale up a lot. Let's say I have 1,000,000 O2s, really big. Well, if I no, I am not going to try and draw that. If I do that, I think I can see that the scale would be consistent. If I have 1,000,000 O2s, then I have 2,000,000 oxygen atoms. And each one of those oxygen atoms would match up with an H2 molecule. So I would need 2,000,000 H2 molecules. And if I had all of that, I could make 2,000,000 H2O molecules. That scale, that 2 to 1 to 2, keeps happening. But I still can't count molecules. I can't count out 1,000,000 molecules. It'd take forever, and I can't count molecules. So how could I make this into something I can actually measure? Enter our friend, the mole. Remember, the mole is nothing more than a big, fixed number of molecules. So I could say that I have 6.02 times 10 to the 23rd molecules of oxygen. Well, if I have 6.02 times 10 to the 23rd molecules, then I need twice as many molecules, or 2 times 6.0 times 10 to the 23rd molecules of H2, and I'm getting really tired already of saying 6.02 times 10 to the 23rd. So let's just remember that that is a mole. And then it's a whole lot easier to just say I need 1 mole of oxygen molecules and 2 moles of H2 molecules, and I would make 2 moles of H2O, which has actually gone right back to the coefficients of my balanced chemical equation. So really, the coefficients in my BCE aren't just molecule ratios. Since a mole is just a really big number of molecules, this is also a mole ratio. Moles are a unit that we know how to relate to grams. We can just use the molar mass. We've been doing that for months. So I could measure out 2 moles of H2. I know that's 4.032 grams of H2. I can measure out a mole of O2. It's 31.998 grams. And then if I put those together and get them to react, I could even maybe capture that water vapor, and I would be able to measure that mass and use the molar mass to figure out, did I make all 2 moles of water vapor that's possible? So let's get back to that mystery bottle of barium chloride, because no, I have not forgotten about it. We need a BCE for this equation. So aqueous silver nitrate solution is react with a solution of barium chloride, aqueous barium chloride. If we think about what would happen here, the silver would have to match up with the chloride ion, and that would make AgCl +1 -1. And the barium would match up with the nitrate, and I would in fact need 2 nitrates to get 2 negative charges to balance out my 2 positive charges. And since I know that nitrates are always soluble, this must be aqueous, and the silver chloride should precipitate. That means now that I know that these coefficients are a mole ratio, I could read this to say that I need 2 moles of silver nitrate for 1 mole of barium chloride. 2 moles of silver nitrate per 1 mole of barium chloride. You know what that sounds like? That sounds like a conversion factor. Think back to early this fall. We said we had 1,000 milligrams per gram, or 1 meter per 100 centimeters, or, well, 2 moles of silver nitrate per 1 mole of barium nitrate. So I could maybe just use the exact same methods that we learned back in the fall with conversion factors to use this mole ratio to help me predict how much silver nitrate I need. Let's see how that would work. So let's assume that this is probably likely to be somewhere around 0.1 moles of barium chloride. That's a really common molarity in my stockroom solution, so it's a decent guess. How many moles of silver nitrate would be needed to react with 0.1 moles of barium chloride? And I just saw the words how many, which makes me think I need a question mark. Let's set it up just like we did in the fall. Question mark moles of silver nitrate is equal to, would react with 0.1 moles of barium chloride. Then I set up my conversion factor, or my railroad tracks. Remember, we get that conversion factor, that ratio, right out of the balanced chemical equation. It's 2 moles to 1 mole. So if I set this up, I'm going to put the unit I want on the top, the unit I want to cancel on the bottom because we need our units on opposite sides of the fraction bar. And really intuitively, you could probably think about it and realize that if it was a 2-to-1 ratio, I would need 0.2 moles of silver nitrate to react with 0.1 mole of barium chloride. If I know how many moles I need, well, I can get back to something I can measure. That's just using the molar mass again. So before you go, I'd just like to do a little proof of concept and make sure that this reaction actually does work. So I have a little video for us to watch. So just as proof of concept, I put some of the barium chloride solution into this test tube, and we can see that it is colorless and transparent. Now I'm going to add some drops of silver nitrate solution, and we'll see what happens. We can see that the solution immediately became white and opaque, which tells us that we now have a suspension, a heterogeneous mixture. So we have made a precipitate. There's a solid in here. And if we wait, the solid will settle and we will eventually be able to filter this out. So our reaction indeed makes a precipitate. Now you can see after I've given this some time to sit, the solution is still a little bit cloudy, but you can see there's a lot of the precipitate, the solid, that's now sitting at the bottom of the test tube. And this means that this is now a solid that I could use a separation technique like filtration to remove from the liquid. Then I could measure that, and if I know how much silver chloride I made, then I could use the mole ratio to find out how many moles of barium chloride did I have to make that amount of precipitate. This is a basic stoichiometry problem, which is our Unit 6C. Okay, so we will indeed make a precipitate. We can use the balanced chemical equation to predict how much of something I might need to react. We can also use it to predict how much product I might make in a chemical reaction. And that's what we'll be doing as we move forward in this unit.